Hi, good afternoon. I'm in the unenviable position of following the dynamic Tom Sterling to the podium. So you can go back to sleep or get some coffee now. I'm talking today about some of the things that actually Thomas alluded to, which is advanced networking and intelligent systems engineering in particular is being applied to the network layers of the system, but also in reference to our new departments. So in general, my work considers this space. Networks are fast, getting faster. Some of the fastest networks in the world are managed from, in fact, within this building. And I think it's inarguable that networking has impacted computing and really everyone's lives in ways that can't really be overstated. But throughout the years, despite the fact that there are continuing advances in network interconnects, physical interconnects, the protocols that run over them, the application programming models that allow us to use networks, network performance is still an issue. They are getting faster, but they are not getting faster in ways that allow the use of them to keep up with increases in computation. And constantly there are issues around how fast you can move bits from one place to another. So bandwidth can be solved with cost of some sort. You can pay money, I like to say, to really just increase the link speed, to put more links in parallel, bond them together in some way. That's an easy problem. Latency, as Thomas alluded to, is a little more of a problem. The speed of light has not changed, and so despite increased bandwidth, there are concerns with physical propagation time. Often even more importantly are software overheads that are not necessarily obvious, but which have a tremendous impact on effective latency. And as soon as there's signaling, really, which is almost all the time, the effects of latency begin to impact the effective bandwidth. As long as there's arbitration, something is telling you can go ahead, that latency starts to matter again, and so it drives down even our ability to use the bandwidth that's available to us. So teasing performance efficiency out of a network system is the job that we have. That's the work that we do, and it involves techniques that span various architectural layers, components of the system that really cross traditional boundaries, as again Thomas alluded to just a moment ago. I probably should have asked him what he was going to say, since his office is a few feet away from mine, before I came and said the same things. But you heard it from Sterling. It's true. These problems are not solvable by considering an improvement at a single layer, but really it's a vertical integration that we have to undertake. So a theme in our work is programmable and adaptable networks. And I've been saying for years, if there's something in there we can program, we want to program it, because currently sort of networks are considered to be, by design, just passive movers of bits. In fact, for some time it was anathema to consider intelligence in the network. The end-to-end argument, which drove the architecture of the internet, was predicated around the fact that the end had to be simple, that the middle had to be simple, all complexities at the end, and processing in the middle was just a no-no. Well, we don't agree with that, so we like that, programming in the middle. And programming, so we consider things like software-defined networking, which is a huge trend that allows you to have fine-grained control over the data plane, over the forwarding infrastructure. Smart network interfaces, which allow us to do things like move data in and out of a system without interrupting the CPU, allowing it to continue to do its work. And network processing elements that can be adapted to make environments like the Internet of Things work more efficiently by doing in-network summarization and analysis rather than shipping great wads of data to the cloud to perform simple calculations over it. We can do that in the network, very close to the edge, with greater efficiency. And field programmable gate arrays, as again Thomas mentioned. So each each of these allows greater efficiency, allows us to improve performance in various ways. Realizing them again it requires customization across various layers, across various components, various traditional sort of domains. That's my bell? Okay. Well, I was about to get to the one thing that he hadn't said. So now look, the traditional curve, as my friend Andrew Lumsdaine would say, it goes up and to the right. That's what we like. It's improving performance. That's a 10 times performance improvement. When we were able to put critical elements of parallel computation on the network interface implemented directly in the FPGA with a sort of vertical integrated system. And that's my story.